It's like, okay. Okay, so it's 11 a.m. and we must start on time, so we will start. So welcome to Chai and Why. For those coming for the first time, this happens on the first Sunday of the month at the Theatre, third Sunday of the month at Uparel College, which may change next year. And fifth Sunday of the month, like this month has a fifth Sunday, we will be live from a lab in DIFR. That's an online only session. Today, it's a pleasure to have with us Bihan. Bihan is a researcher in the Department of Astronomy and Astrophysics at DIFR, where he is working for his PhD in the area of exoplanets. And Bihan comes from somewhere near Kolkata. He did his BSc there, then went to IIT Guwahati for a master's, and then joined DIFR for a PhD program. And he's going to tell us today about some very interesting planets that orbit other stars very close to them. And to tell us more about that is going to be Bihan. Now, for all of you who are watching us online, and I see more people on than here, please remember that the only way you can interact with us is through the chat. So please put your questions and comments in the chat, and we will, take them and you can ask Bihan the question and he'll answer them. Okay, so on that note, I think you should share your screen now, and then we can go ahead. So you can share screen now.
Yeah, thank you.
So
yeah, I will start.
Slideshow. Yeah, please. Okay, we can do that. Slideshow. Yeah, and then you can write through. So, we have a density video. Okay.
Yeah. Thank you everybody for coming here and joining here today. I will be talking about exoplanets who are very dangerously very close to their stars, and how their life is, and how dramatic it is, and how different from our known planets they are. So let's start with something very familiar to us, which is the solar system. We know we have seen this system from our childhood. We have sun at the center and 8 planets which orbit them, and we are in one of the planets. We are on one of the planets, which is here. If you can see my cursor. Now, and the solar system has a peculiar configuration. There are small planets in the inner system and large planets in the outer system. So this is one very particular feature about solar system. This image is of course not to scale, and this is in logarithm scale, and you will see that in logarithm scale the inner planets are the closest one, which orbits the Mercury orbits the sun about 80 days or so, 88 days, and the outermost planet is around 30 AU, an order of magnitude variation of the orbital distance. But however, beyond all the 8 planets, there are other objects, which some of which are in between Jupiter and Mars, and some are beyond Neptune's orbit. Anyways, but Sun is one of the stars among billions of stars in our galaxy. What about other planets? What about other stars? Do other stars also have planets around them? Now, this is a question that human beings have asked for decades. because it is the nature of human beings to ask questions. Now, as early as ancient Greece, Greek philosophers discussed about ancient arts, but these were only, they just sat and spoke about it. They didn't have any techniques. It was all hypothetical. And one of them was Epicurus, who conjectured that there can't be one earth, there should be earth analogs. And it's somewhat similar to what people talk about multiverse today. But there were no means to detect other earths at that time. However, if we move forward in time, in 1592, it was Renaissance in Europe. And one Italian mathematician came up with many revolutionary ideas. One of them is this. There are countless suns and countless earths, all rotating around their suns in exactly the same way as the 7 planets in our solar system. 7 because at that time only 7 was discovered. Neptune was not known. However, Bruno pointed out why we see the stars but not the planets. And he identified the problem. Because the stars are very, very luminous and the planets are very faint. That's why we can only see the stars but not the planets. Bruno said this and many other things which the church didn't like very much. At that time, it was not a good time to be doing exoplanets. Bruno was burned at stake. However, his ideas were not burned. Those remained, and human beings continued the pursuit of this question. And many years passed, and we still don't have even in 1900, we didn't have signatures from planets. However, Bruno said one very important thing. It is very difficult to see the planets because they are very faint. It is important to focus on the stars because they are luminous. Now, what can we know from the stars? Now, if you see the star in a sky, what we can do are roughly 3 things. One, we build telescope, we collect the light from the star. You can imagine a telescope like a big bucket. You fill the bucket with all the light that are coming, and you then measure how much light have you collected. The other thing you can do, you can put a prism in front of the incoming light, and that will be dispersed in a spectrum. And you can study that spectrum. How different, in different wavelengths, how many photons are coming. Is there any emission or absorption lines? And the other thing is looking at the star, monitoring the stars very, very precisely and measuring its motion. So if I hold my arm like this and observe the thumb with my right eye, and then close the right eye and observe the thumb with my left eye, there will be a small shift. And if I know the distance between my 2 eyes, I see the shift with respect to the background, which is not shifting, I can find out the length of the arm. In the same way, we can find out the distance to the star. So the first technique, collecting all the light that are coming from the star, if I combine these two, we can actually find how bright are the stars. And from this, we can find out how hot is the star from the spectra, because the spectra depends on the stellar temperature. And if we know the total luminosity and temperature, we can construct something called the HR diagram, and different types of stars line up in different positions in this diagram. The most common stars, which are called red dwarfs or M dwarfs, are here. Sun is about around here, and there are all sorts of stars. So and from here we can find out stars' mass, stars' radius, and all the relevant properties. So this much we can do from the stars. As astronomy progressed, we learned these things. However, let's come back to these questions. Do other stars have planets as well? Now we come to 1952 and come to this gentleman, Otto Struve, who was a Russian-born American physicist. At the time, in 1950s, binary stars were already known. Binary stars, Sun is a single star, but there are stars which are not single. They are gravitationally bound with another star. So they go around each other. And as they go around, two things happen. When one star goes behind the other star, there is a dip in the light. And depends on how bright two stars are, etc. But if you can't distinguish two stars, you collect all the light from the stars. When one hides behind the other, there is a drop of light. And again, when it comes out, the flux increased. If the two stars have different brightness, the variation will be different. Other thing is, there is also, if we are aligned to this motion of the star in a certain way, if the star moves towards us, the spectral lines that we see here gets shifted towards blue. And when the stars move away from us, the spectral lines correspond to that star shifts towards red. One simple demonstration using sound can be shown, which is sort of like this. Can everyone hear? Now, if I rotate it like this, when it comes towards you, you can hear a high-pitched sound. But when it goes away from you, you can hear a low-pitched sound. If I do it slowly, it is difficult to detect. But if I do it very fast, you can detect, right? This is the same thing, same technique applied here. But this was only done to stars. Stars are very massive object, and binary stars also are very close to each other. So the gravitational pull was quite high. And the shift that it generated was enough to be detected using the spectrograph. But he suggested something remarkable. But what if instead of a binary star, there is a star and a planet? The planet will still pull the star. If there is a star and a planet, the star will also wobble a little bit around the common center of mass. And that will cause some radial velocity shift. He calculated if there is a Jupiter mass planet very close to the star, this shift could possibly be detected in future spectrograph. And also the Jupiter sized planet will cross the star, and as it eclipses the star, that drop of light can also be detected. But at that time, in 1950s, everyone sort of said, you are imagining Jupiter size and Jupiter mass planets so close to the star. It can't happen. Because we are so biased with the solar system that we have our Jupiters far out. It can't be as even closer to Mercury. So everyone rejected that idea at that time. However, this trying to build better quality spectrograph continued, and that finally people started this hunt for exoplanets, trying to build better and better radial velocity spectrograph. The idea is the same. When the star moves towards you, there is a blue shift, and when the star goes away from you, there is a red shift, and you try to detect that shift. The more massive one planet is, the larger will be the pull, and the larger will be the shift. But how large is the shift? Now, if we look at our solar system, then for Jupiter, this shift is only 12.5 meter per second. And for Earth, it is even less, centimeter per second. Now, these are extremely difficult to detect. Even around the 60s and 70s, the best spectrograph in the world could detect the shift which is of the order of kilometer per second. But here we are talking about meter per second and centimeter per second shifts. So everyone tried a lot, but they couldn't succeed for a long time. But they continued developing better and better spectrograph until in 1995, there was a sudden breakthrough. Everyone, when earlier was looking for planets which are analogous to Jupiter, that is a massive planet, but quite far away. So the signal should be around 10 meters per second. However, what they detected was something that Otto Struve suggested, which is a Jupiter-like planet, but very close to their star, and therefore very hot, and we call them hot Jupiter. And these two gentlemen found it, and initially everyone was skeptical, but soon a very beautiful the radial velocity curve was found in follow-up, and it was confirmed, and they were awarded Nobel Prize in 2019. So, however, in this regime, trying to detect planets using radial velocity, there is effort from India also. India is also in the game, and this is Mount Abu Observatory, which is under PRL Ahmedabad, and I was fortunate to go there for a conference this year, and this is the telescope with which radial velocity spectrograph is attached. So this is one method that I talked about. There are a planet and a star, and the planet pulls the star because of its mass, and more massive the planet is, the larger will be the pull, hence larger will be the velocity shift. From that you can determine planet's mass, but there are two uncertain parameters. You don't know what is the velocity component. You don't know how the orbit is aligned. Is it exactly edge on? Is it little bit inclined? There is that uncertainty. And you don't know anything about the size of the planet. The other way is to keep looking at the star. If there is a planet around it, it may cross the star, right? For example, suppose focus here. Take my hand like this. There is a drop of light from here. And similarly, if a planet crosses the stellar disk, there will be a sudden drop of light. And as a result, you will, and if that happens periodically, because a planet rotates around the star and comes back and rotates again, and if that happens periodically, you may conclude there may be a planet. This depends how much this drop in light will be, depends on the planet's area divided by the stellar disk. And for Jupiter, this drop is only 1%. So, and for Earth, it is even much smaller, almost 0.01%. If you take your phone and try to reduce its brightness, make it full bright and try to reduce its brightness, and see after how much reduction your eyes can detect there is some change, and you will find it is quite large. So detecting this much drop in light is very difficult in human sense, but the humans have developed certain instruments which can do this, and Kepler Space Telescope for this mission, for this transit, was launched in space. So from ground-based, there is a difficulty because there are two difficulties. For transit observation, you want to keep looking at one particular star, but in Earth there are day and night problem. In days you can't observe, and then there might be some clouds crossing along your line of sight, and you might think, oh, this must be a planet, but then you so the precision is less from ground, and Kepler was launched in space, and it discovered thousands of exoplanets. And now Kepler is decommissioned. It from 2009 it was there in space till 2012. Then there was some problem, and eventually it was decommissioned in 2016. And now TESS is there, which is also doing a transit survey. So these two methods are indirect methods. We are not looking at the planet, we are looking at the star and trying to detect what effects do the planets induce on the star. However, the most straightforward method would be if we could click a picture of the planets. But it is very difficult. It is difficult because it's like trying to click a picture of a firefly in front of Wankhede floodlight. You will only see the floodlight. You won't see the firefly. Star is so bright. The planets around, if the planets are pretty close to it, it's very difficult to see them. So the only way we can see planets around a star directly, if we can somehow block the starlight and then see if there is something bright around. Now, we know that planets do not have their own light, right? They reflect stellar light. Now, if we do the same thing here, the contrast ratio is not so good. It's difficult. But if we try to see some young and hot planet, which has some temperature, which also emits, those planets are easier to detect by this method. And those planets has to be much, much far away from the central star in order to detect them. And this was one fascinating system, HR8799, which were observed from Keck by a group of Marines. And they followed it up, and you can see the planets go around the star quite nicely. So this is the first time, not the first time, this is one of the remarkable things that we are looking at the other planets going around other star directly. But these are quite massive planets and far, far away. The other methods, so far, the radial velocity and transit method are the most successful ones. But you can imagine if the star is moving in planet's pool, radial velocity is applicable when you are viewing the system edge on. That is, at one point of time, star is coming towards you and then going away from you. But it can so happen you are viewing the system face on, and you are trying to see how is the star moving directly. Instead of seeing the spectral shift, you try to locate the star and how it's moving. And that is called astrometry. And Gaia is a satellite which locates the position of the star and the motion of the star, records it very, very precisely. And 1 degree in this plane would be this much, very small. If you divide 1 degree by 60, that is 1 arc minute. If you divide that by 60, that is 1 arc second. If you divide that by 10 to the power 6, that is the precision in which this satellite can detect a shift. So, radial velocity exoplanets and transit exoplanets are dominating the field right now. But in early next year, not next year, 2026, I mean, in 2026, Gaia will revolutionize the field with detecting more than 10,000 exoplanets by this method. However, the first exoplanet detection didn't come from any of this. It came from a very rare place, from an object called pulsar. Pulsar are strange objects which are very magnetized, rapidly rotating neutron star. And you can think of it like a lighthouse. It emits a beam like a lighthouse. And if that beam somehow are pointed towards us, we see that pulsar. However, their rotation is very, very precise. They rotate in exact same rate. So, if you note, if you didn't note the time when the beams are arriving, they are very, very precise. However, if there are planets around, and if the planets make the pulsar go back and forth, the arrival time of the beams will change. And a group of scientists discovered that in 1992 and concluded there must be planets around that pulsar which are making it move back and forth. Because the shift was consistent with the planetary mass objects. But this is a very rare system because a pulsar, which is a dead star, a star goes supernova, dies, and the remnant becomes a pulsar. After that explosion, it's very hard, it's almost unlikely for any planet to survive. So people conjecture that maybe after the explosion, these planets have been formed. These planets have formed, but this is very, very rare. The other method is microlensing. If something goes in front of background star, the gravity of that object sometimes acts as lens, and that magnifies the background star. If this star has a planet with it, it magnifies even further, and from that you can, from these two peaks, basically you can find if there is a planet around the star. Now, yes. Yes.
One is when we are seeing it edge on, so the planet is going to get and see behind the star, but if it is face on,
yes.
Face on with respect to our line of sight, so it's going this way.
Yes.
Right? How
yes.
exactly?
Yes. How do we know? Okay. Right. Exactly. So the two ways are, if the planet is really far away, you can try direct imaging, and if the planet is big and it emits significantly, you can do direct imaging. The other way, you try to detect the star's motion itself. In radial velocity method, you try to detect the Doppler shift, right? But here you measure the star's position with respect to time. As the star will move around its center of mass, it will make a tiny circle, tiny ellipse, and you try to detect that tiny motion. And it is very difficult experiment, but Gaia has a sensitivity which is able to do it. So instead of looking at the motion by Doppler shift, you look at the star itself as it makes the tiny ellipse on the plane of the sky. Yeah, does it answer the question? Yeah. Yes. 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 Gaia is operating in space. Gaia is launched a few years ago, and the goal of this mission is to map the Milky Way and to have a very precise location of each of the stars in our galaxy. Very precise location, very precise movement of all these stars. Yeah. Now, so I was born in 1996, and at that time, very few exoplanets were known. Because the whole field started in 1995. And in 30 years, the field has exponentially grown, and now it's almost 6,000 planets, and there are so many missions coming up. So it is a fascinating time to do exoplanets. Very in contrast to the time of Bruno. Yeah, so many planets have detected. Now, let's talk about some of the exotic features of the planets that we have found. Now, what is remarkable is that because both the transit and radial velocity method are the two most successful methods so far, are sensitive to the planets very close to their stars, we find some very hot planets. We find giant hot planets, we find small hot planets. 55 CNCE, people predict this planet is so hot that there is magma everywhere on the surface of this planet. Hot Jupiters are also a very puzzling thing when it was found, because is it formed there? This big planet, is it formed at their location, or have they formed outside or migrated inwards? All sorts of questions were asked. What was also very interesting was a class of planets which are bigger than Earth but smaller than Neptune's. And it turned out these are the most common planets in our universe. However, our solar system doesn't have one. We have Earth, we have Neptune, we have nothing of the size in between. The question is why? And we still don't know a perfect, well-rounded answer to that. And we are interested of what are the super Earths made of? Are they rocks which have grown big? Are they big ice giants which have grown smaller? Or are they something completely different? How many of you have watched Star Wars? Okay. So do you remember the planet Tatooine in the film New Hope? So there are two stars, right? And there is an exact system like Tatooine, Kepler 16b, which has two stars. And this planet goes around both of the stars. And this is NASA JPL's poster for Kepler 16b, because you will always have two shadows on the surface of the planet. There is another remarkable thing. We have discovered some very compact systems. Mercury goes around the sun in 88 days. This system I am about to show you, their outermost planet detected so far goes around the star in 42 days. That is the outermost planet. Okay. Yeah. And there are this system, the K2138, were found by citizen scientists, common people. So the K2 data were given out to people, and they asked for help, and they helped, and they found 6 planets from this system. And one interesting thing is these planets are very musical, because their periods are of certain ratios. When the innermost planets goes around the star 2 times, the immediately outer one goes around in 1 time. So the periods are integer multiples of each other. So if we assign a note to their orbit, it sounds very harmonious. And let's listen to the music of K2 138 system. Okay. Yeah. There are 6 planets. Whenever one planet's transit, there is a bomb. So these are called resonance systems. The orbits of each uh, planet are in resonance with each other, and therefore they sound musical. So this is another example of a very compact system, and it was very interesting at first. It is this planet is called TRAPPIST. This system is called TRAPPIST-1 because there are multiple planets where in such a location they orbit around a very cool star, which are called red dwarfs, which are much fainter and smaller than our sun. Because the star is cool, the place where water can exist in liquid form is also closer. And this is inside Mercury's orbit. So many planets are lined up, and they're all in a place where liquid water can exist. And this is interesting because we always look for planets which are analogous to Earth and where life can exist. And so these planets were first identified as potential life hosting planets. However, this star emits a lot of X-ray and ultraviolet rays, and therefore people are not so sure anymore, not so hopeful anymore. However, we keep looking, that's the motto. So let's take a step back now and look at the whole picture for once. So these were our knowledge of planets at 90s. And since then, people from this planet has known almost about 6,000 exoplanets. And you see, most of them, because of these two methods limitation, they are located very close to their star within 100 days of orbit. There is only one such a system in solar system in that kind of an orbit. And what is remarkable came out of all this mission is that each star that we see in the sky has at least one planet. So, and even more than one. So, number of planets are clearly more than the number of stars, probably. So, it is very unlikely that and also what is remarkable is the utter diversity of the planets. And we see planets of so many sizes, even at the close separations. It is the same thing in mass period plane. Now, since they're so close to the star, it begs the question that how does star treat them? How, because star is a hot object and which emits a lot of radiation, how does it affect the planet? Now, if we look at Greek and Indian mythology, the two characters who flew too close to the sun, one is Icarus in Greek mythology, one is Sampati in Ramayana. And both of them ended in tragedy. So their wings got on fire. So does something like that happen to the planets too? Planets don't have wings, but they have atmosphere. Now, these are all Kepler planets, the planets detected by Kepler. And when these systems were studied further for better accuracy, one interesting thing was found. I already mentioned planets between Earth and Neptune were the most common in the universe. So people were interested in it, and to determine, they were interested to accurately determine their radius. Now, what you detect in transit is basically the planet's radius, the ratio of planet's radius to the star's radius. So if you know the star's radius accurately, then you can lower the uncertainty of the planet's radius. And when people did that, they found that super Earth planets are common, which is roughly 2 times the size, no, not 2, which are roughly 1.5, 1.3 to 1.5 times of Earth. And there was another peak, which was around 2.4, which we call sub-Neptune. But there is a clear gap in between. There are no planets with around 1.7 to 1.8. There are lack of planets with a radius 1.7 to 1.8 times that of Earth. And this was discovered by Fulton in 2017. And from his name, it's called Fulton gap sometimes. And in orbital period also, there is a clear valley. And whenever we see something like that, something like this, some pattern, we try to answer that question, because this is a nice mystery, and why don't we solve it? And one idea is that maybe in the beginning, when the planets formed, there were planets of all sizes. But what is a planet? It has some core, and on top of that, it has an atmosphere. When it transits, we see the whole thing. It's hard to detect, hard to distinguish between core and atmosphere. If the radiation from the star somehow stripped some of the planet's atmosphere, then they will appear smaller because their atmosphere is gone. However, if there are some massive planets which are able to retain their atmosphere, they will appear bigger, and hence this can be explained. This is one of the mechanisms, by the way. There can be many ways this can also happen. This is one of the explanations. But this thing, if planets are indeed losing their atmosphere, can also be observed. And this has indeed been detected by when the planets cross the star. There is a tail of hydrogen and helium of the which is of the evaporating wind launching from the planet. And you can, if you keep looking at it, you will see some absorption lines even after planet has transited. Now, X-rays, now the important part of the star here is X-rays and ultraviolet rays. They ionize the planet's upper atmosphere and eject very high energy electrons. Now, these electrons bombard other atoms, and as a result, the whole atmosphere gets very hot. And once it gets very hot, it starts to escape. And this is the process behind. So, this is one of the work I did during my thesis, is trying to simulate this whole process in a population synthesis model. And you see here, initially, there is an evolution from initial to final state. There is an evolution of the radius valley, and planet's mass radius also keeps changing. And finally, what we observe, the observed distribution, can be reproduced. Now, in the end, even if we begin with a single population of every planet having an atmosphere, we can end up with planets which has atmosphere and which doesn't have. Now, yeah. So far, we are talking about smaller planets. Now, let's talk about giants, Jupiters. Now, back in the day, we knew only one Jupiter, which was very far out in our solar system, and with an orbit which is not very eccentric. That is, they're almost circular. Jupiter's orbit is almost circular with very nominal eccentricity. This is a period and eccentricity diagram. However, now this whole plane is a mess. We see all kinds of Jupiters. We see Jupiters which are very close, these hot Jupiters. We see Jupiters which are cold. By Jupiters, I mean planets which have mass and radius like Jupiter. Planets which are cold but have a large range of eccentricity. Now, we ask this question, are they of the same origin, or does this orbital diversity of Jupiters say something about their formation or evolution? Now, the planets that we see are not there forever. They have a finite age. They form one day, and they evolve and they eventually come to the present state in which we observe. And they form in a spectacular manner. So initially there is a big molecular cloud which starts to rotate, and because of gravitational pull it collapses, and the central object becomes a star, and everything surrounding flattens up because of the initial rotation. Rotation can flatten things up because if you see how a Romali roti is made, it's usually always spinned so that it flattens out. Uh, and this is, and because of the, so initially because of the rotation, everything collapses onto a disk, and in that disk, all the planets grow and creates a planetary system. And these disks actually can be observed. They emit radiation in a very long wavelength. And we have such telescopes which can see structures in the disk, which is a signature of the planets which are forming. These are nurseries of planets. Here the planets are being born now at the very moment. And these gaps are probably, there is a planet in this gap which are eating up all the material and keeping it to himself, herself, and growing eventually. And this is one system where the baby planet is detected. It's imaged like this bright spot. It's called PDS 70. So the planets are formed in this way, and these are probably, these giant gaps are created like Jupiters of like planets. Now, if you want to make a Jupiter, what is the recipe? Let's think. So to create a Jupiter, first you have to collect a large amount of mass, of solid mass. If you collect a lot of solid mass, it can gravitationally attract the gas which are nearby very rapidly, and it will grow as a giant. Now, it's very hard to create such a planet very close to the star. Because imagine a circle, or imagine that you are eating and you have flattened out your rice, and if you collect the rice from the outer part of your plate, there will be naturally more rice, and if you collect as a ring from the central part of your plate, there will be little amount of rice. So it's easier to form giant planets at a larger distance. Now, if a giant planet is formed at a larger distance, it is forming in a disk, and it can exchange angular momentum with the disk and eventually come inward. The other way, if there are two giant planets formed in very close separation, one can send the other in a very eccentric orbit. And if it is eccentric, at one point it will come close to the star. And star will, by tidal force, it will compress and stretch the Jupiter. As a result, Jupiter will lose some energy and eventually lose their orbital angular momentum and settle down in a smaller orbit, like shown in this image. Here, a cold eccentric Jupiter is migrating to a very hot place closer to the star. And this can take a long time, millennia to a billionaire. However, in our study, we tried to see if this is indeed happening by comparing the stars of different types of Jupiters. And what we found is that the amount of solid which are locked up in a star sort of connects to the amount of solid which were initially available in the disk. And we found that in that sense, hot Jupiters and cold Jupiters which are orbiting in eccentric orbit are very similar. But on the other hand, hot Jupiters are very young compared to the other type of Jupiters. If hot Jupiters and cold Jupiters which orbit in eccentric orbits are of the same origin, we expect all their properties to be same. but we find hot Jupiters are young, as if older hot Jupiters are removed from the system. Now, how can this happen? Now, let's take a look at Earth and Moon system. We know Earth spins around its axis in 24 hours, and Moon goes around the Earth around in 30, close to 30 days. However, Earth spins very fast and Moon spins slow, and Moon orbits slow. And as a result, there is a tidal interaction. There is already a tidal interaction between them. But because their spin and orbital angular momentum are different, there is a lag. Earth spins fast and Moon lags behind. As a result, the tidal interaction tries to speed up Moon and slow down Earth. And as a result, Moon is pushed away every day, 1 inch in every year. 1 inch in every year. It's not a huge amount, but Moon is going away from us every day. The same thing, actually the opposite thing can happen for a hot Jupiter star system, because hot Jupiter spins very rapidly and the star spins slowly. There, the hot Jupiter will try to spin the star up, and as a result, hot Jupiter will lose some angular momentum. And as a result, hot Jupiter will move inward to the star. And as a result, some hot Jupiters may fall into the star and be lost forever, and we won't be seeing them. So this is something what we found. Older hot Jupiters might be getting engulfed by their star. So as a summary, we see a lot of exoplanets in short orbits, short orbital distances because of observational biases. However, we find something very diverse and very different compared to the solar system. And because of their close proximity, their life is very dramatic. A lot of exoplanets lose their atmosphere. A lot of exoplanets get eaten by their star. And there is so much more to explore. And this is the golden age of exoplanet exploration. And anyone can find a new type of exoplanet. And thank you. Yes, please.
Maybe I'll come close to you so that the audience can also hear that I'm repeating the questions.
Yes.
So the first thing I think concerns our own Jupiter.
Yes. Right.
Solar system Jupiter. Is it really a failed star?
No, we can't call it a failed star. A failed star because our Jupiter never aspired to be a star. We actually called something more massive a failed star sometimes, which are brown dwarfs, which they are 13 times Jupiter mass. They can burn deuterium in their core, but Jupiter is not that massive, and it is also it orbits around our sun, and it's very planet-like.
So Jupiter is still too small for nuclear fusion to happen.
Yes, yes, yes.
Then there is a question from Sanjay. Are hot Jupiters really gaseous?
Yes.
And what gases are they made up of? Are they similar to Jupiter in terms of being hydrogen, helium, methane, etc., or are they different?
Yes, hydrogen, helium are surely of the highest amount. They are different in some ways. Their sizes sometimes are much more than what you expect to be a given mass, because it can happen something to do with the stellar heat. They get inflated sometimes, and also they lose some of their hydrogen and helium atmosphere because of their close proximity to the star. But yes, their composition wise, they're mostly made of hydrogen and helium.
Okay, so they're mostly hydrogen and helium.
Yeah.
Okay, and then there is a question about is TIFR detecting exoplanets? Continuation of the question is India as a whole detecting exoplanets?
Okay.
And
so,
if so, which method?
India has a dedicated radial velocity instrument, which is in Mount Abu, and this is the observatory, and this is the telescope. This only tries to detect exoplanets using radial velocity. And there are reports of some detections as well. And TIFR is independently so far have not detected, but there are instrument building. And there is one method which I have not mentioned, is looking at exoplanets in radio wavelengths. That group in TIFR is doing. My senior Mayank is leading the effort. He is now not in TIFR, he is senior of mine. But the idea was, if we look at our solar system in radio wavelengths, the most bright object is Jupiter, apparently. And the reason is Jupiter has a large magnetic field, and a moon called Io, which has a lot of volcanism. So all these volcanoes erupt, a lot of charged particles, they get trapped in Jupiter's magnetic field and emit as a cyclotron emission. And solar wind also gets trapped in Jupiter and gets emitted in radio. So using GMRT, we tried to detect radio emission from other exoplanets and tried to use it as a probe for exoplanet detection. But so far, the result is null. There is upper limits placed. There are upper limits placed, and there are possible detection from distant cousins of Jupiter's, which are the failed stars, the brown dwarfs. But in near future, this might be another good field, because square kilometer array is coming up, which is much more sensitive to detect exoplanets in radio. And this one way you can also constrain the magnetic field of the planet, which is really interesting.
Okay, so we take questions that would tell me there are interesting questions, so let me take them.
Yeah.
This one's really interesting. Why is studying the atmospheres of exoplanets crucial, especially for understanding their habitability?
Yes, so this is something I did not talk about much, but yes. So if we look at the temperature, only the temperature of a given body, it depends on many things. For example, at 1 AU distance, when Earth formed, probably there was no water. But Earth's atmosphere is such, atmospheric pressure is such that water can, atmospheric pressure and temperature are such that water can exist in liquid form. And also, atmosphere contains, when the planet transits and starlight gets absorbed in the planet's atmosphere, from that we can say what are the atmosphere made of. Are they made of mainly gas, like are they made of mainly with hydrogen or helium, or are there water, oxygen, methane, some biomarker like gas, ozone? And also, studying the atmosphere, we can constrain the temperature and pressure profile inside the atmosphere, which is which is very important to say conclude something about habitability.
Okay, there is one more provocative question, but before that, I'll take a question which is simpler. Hot Jupiter is made up of what?
Hot Jupiter is made of mainly of gas. Their core.
Gases of high relevance,
the gases of hydrogen and helium.
Hydrogen and helium. Okay.
But their core probably is solid. That we don't know, but we assume from the structures of Jupiter that their core is probably solid, and outside there are hydrogen and helium.
Okay, now the last one we'll take is this interesting one. Even if we find out about exoplanets, they're very far away.
Yes.
How does it help us?
Well, they give us perspective, I guess. And but yeah, they are very far away. But not everything helps us. I mean, help in what sense? We ask questions, we wonder, we try to find answers about them. That is the fun of doing science. The application may come later.
One question is, might studying exoplanets help us understand climate change on Earth? Repeat the question.
Studying exoplanets might help us climate change on Earth. I think Earth's climate study will be more beneficial.
Okay, so I think that takes care of the online questions. We can see the questions that we have.
Yeah.
Yeah, we can do that. So we can yeah, I will announce the next. Can you stop sharing?
Right.
Yeah. So thank you, Bihan. Thank you for your telling us all about the exoplanets. You can turn some lights on, I think, now. Before we end the online streaming, let me tell the viewers about our next two sessions. We have a 5th Sunday in December, which means we have a light from the lab session. And this is going to be from the quantum materials lab in TIFR, where they have what is called a molecular beam epitaxy system, where they can deposit atomically thin layers of different materials, one on top of the other, and study all kinds of exotic properties. So we will be visiting that lab on 2 weeks from now. So it's 29th of December. Following that, we will move into 2025, and the first Sunday of January 2025 is a rather special Chai and Wai. It will be at Prithvi Theatre. We have a chaired professor at DIFR, Professor Subir Sarkar from Oxford, who will be coming. He's a cosmologist, a very well-known cosmologist, and he will be talking about the sort of evolution of the universe and everything that there is in cosmology today. So that's happening the first Sunday of January 2025 at Prithvi. Okay. So thank you. Keep watching us online. If you're in Mumbai, please come to our sessions. Even better, you get chai. So at the risk of not providing chai online, that's only going to be for people who come here. We will end this online session, but audience here, you can continue with chai and questions. Okay. And thank you, Bihan. Thanks again.
Thank you.